Hello, my people. I hope we're doing well today. As promised, I'm gonna post a new video along with some of the older ones from Virtual Fourth on the indefinite integral, the thing that we spoke about um, on Friday. Of course, we did a little bit of definite integral as well. That's largely because this chapter is about two topics. One is the indefinite integral, which is what we did a whole lot of. Basically, the same procedure as anti-differentiation back in 4.9. And the second thing is that this chapter is about what's called the net change theorem, and that will be basically the assignment. That will be our discussion on Tuesday and the assignment that is due for Friday. But it involves the definite integral. And so basically the chapter kind of mashes those two together because neither of them warrant a section in the book in and of themselves, but together they make up just enough material so that they can warrant actually making a section out of it. So sometimes you get that in a textbook. You sort of get these things that are sort of cobbled together because they're not quite robust enough to be a unit in and of themselves, but whatever. But let's go ahead, since there's not a whole lot of conceptual stuff going on in this, let's go ahead and just start with a bunch of examples. Okay? And so we'll start with a polynomial one. After the weekend, get the cobwebs knocked out of our head. I hope your weekend went well. Hope you got a little bit of rest. Hope you didn't have to do too much work for all this. Okay. So basically what we have here is we have a polynomial, and therefore what we're going to need to do is, first of all, we need to do it term by term, okay? And second of all, we need to do it, especially with the first three terms, with the power rule in mind, okay? And so we need to ask ourselves when we integrate, and of course we could, split this apart into something like this. And functionally, this is what we're doing in our head. We're doing this in our head. We just don't need to write it down every single time, okay? So basically, when we do the first term, we need to ask ourselves, what is the antiderivative, or what's the integral of t to the fourth? And it winds up being t to the fourth over 4. What is the integral or antiderivative of t squared? And that would be t cubed over 3. What is the antiderivative of t? And that would be t squared over 2. And the antiderivative of a constant is just the variable. Now, I am not finished because like when we did antiderivatives, the indefinite integral basically needs this constant right here, okay? Because what it's asking you is, this expression in the integrand, what is it the derivative of? And it's not just the derivative of these terms right here, it's the derivative of these terms plus some constant. And it could be 2, it could be pi, it could be 13 billion. It doesn't really matter. You just need to make sure you put the plus c out there in order to acknowledge that that plus c is part of the answer. Now all we have to do is just go through and just do a little bit of simplification. That winds up being 1/2 t to the fourth minus 1/3 t cubed plus 3/2 t squared minus 7t plus c. And that is our answer for that one. Now that shouldn't have been too much of a surprise, okay? That one was kind of a Mickey Mouse question. But let's go ahead and let's try and just make them a little bit harder each time we progress. Let's say I have x minus 1 over x squared dx. Now, that's a little more complicated, largely because we're not going to be able to accomplish the integration from the form that it's in right now. You can't, basically with the skills that you have, and in fact, it wouldn't even be, even if you could do it another way, it wouldn't be prudent to do it another way. You need to go ahead and actually expand this out because the term by term is sort of nullified by this squaring right here, because this is really not x minus 1 over x. This is x minus 1 over x squared. So it's actually another expression that is the integrand that is actually being implied right there. Now, when we FOIL it, we have the first, and then we have the outer and inner. Now, the outer and inner are both going to be x times negative 1 over x. So it's going to be negative 1, which gives me minus 2. And then last is going to be that. Now, it seems a little bit bizarre, but whatever, okay? And the thing is that you're like, oh, well, maybe that isn't actually what it is. Maybe you made a mistake, Mr. Forth. Well, remember that this is actually that, right? If I wanted to look at it in its unsimplified form. And if I were to FOIL that numerator, I would get x to the fourth minus 2x squared plus 1. And if you were to square the denominator, get x squared. And if you were to then simplify this, you would get that as well, okay? So either way you want to do it, you're going to get basically the integral of x squared minus 2 plus x to the minus 2 dx. Now, when I do that term by term, I'm going to need to use the power rule, okay? And therefore, I'm going to have, what is the antiderivative, or what's the integral of x squared? 1/3 x cubed. The antiderivative of a constant is just that constant times the variable. And then if I want to add 1 to this, I need to basically, it's x to the negative 1 over negative 1, so minus 1 over x. And then we just have to tack on the plus c just for good measure. Okay? Now, the problem largely for these is not going to be the actual integration. Oftentimes the difficulty is, okay, well, what I have is not in a form that can be integrated right off the bat. How then can I change the form such that it actually is capable of being integrated? Making sure that it is integrable, which I know is a difficult word, it kind of gets garbled in my mouth, but all right. We notice that basically you have two binomials multiplied by each other. In terms of what you know and the skills that you have, this, you can't do it, right? And in fact, there's no special thing for this. You just have to multiply it out. Okay, so you're going to get 6x squared, and then the outer and the inner. So you have negative 15 and positive 2, so minus 13x, and then minus 5 dx. From here, now that it's in polynomial form, now that it's actually expressed term by term and not those things implied by this product, I can go about going ahead and doing the integration. Now, x squared, when you integrate it, becomes x cubed over 3. And I'm going to go ahead and continue to do it like this and then simplify. But if you're to the point where you don't have to do that, that is fantastic. Go ahead and skip that step. I'm proud of you. Rah, rah, rah. Okay. X becomes x squared over 2. Basically, no variable becomes x. And then, of course, you have the plus c. This winds up being 2x cubed minus 13 halves x squared minus 5x plus c. And that right there is your integral. Okay. Now we've done a couple of problems and we've changed the form a little bit, but they've all been polynomial based, or at least power rule based. Let's go ahead and move on to a couple that might actually be a little more, I don't know, I was going to say interesting, you'll probably say frustrating. Let's go at, ooh, I like that one. All right, let's do one more that is polynomial. Now, again, I need to change the form. But the question is how to change the form, right? So I want to look at this and say, well, you know, I really have and don't you dare cancel terms. Okay. in order to cancel factors, and no factors are actually visible here. Oh, sorry, my bad. There you go. Again, let me reiterate now that you can actually see it. Don't you cancel terms. You can only cancel factors, right? And since no factors are visible at present, what we want to do is we want to, of course, then factor it. And I hope that you remember your factorization of the difference of two cubes. If you don't, then rememorize it. Is it fair game for changing the form of an integral on this test? Absolutely, okay? Now from here, you would go ahead and cancel out these factors, right? And simplify this down to x squared plus x plus 1 dx. Now, I'm not going to go ahead and do it. It's actually very, very similar to the ones that we've already done, but I at least wanted to do one of these problems where the change of form had to deal with factoring and canceling, because we hadn't done one of those yet. Now, let's go ahead and move on to ones that are, I don't know, I would say a little more interesting. Okay, now we have the integral of root t plus cosine t dt. Now, this is term by term, okay? You actually can do this term by term. The only thing that might actually be beneficial is, explicitly to turn this radical into a fractional exponent. And having done that, you recognize the fact that this is just going to be power rule for this term, and of course trig for this term. And so when you get t to the 1/2, it's going to be t to the 3/2 over 3/2, or multiplied by its reciprocal. And then you ask yourself, what is cosine the derivative of? And I hope you recognize that that is sine t plus c, and that winds up being your integral. Okay, I'm going to sort of pick up the pace a little bit here, and of course if you have any questions when we come together on Tuesday, you can ask them then. But I'm going to pick up the pace a little bit here so I can get a few more examples in and not make this incredibly long. Okay, well, let's do another trig one. You have secant t over cosine t dt. And you're looking at that and you're thinking to yourself, I know that that is in a rational form, and if it's in a rational form, there's only a couple of different things it can be. It either simplifies such that the rational form disappears, it is a natural log function, or it is a inverse trig that needs to be done, okay? So we look at it and we go, well, it's not inverse trig because the denominator, not only is it trig, it's not two terms, right? It's not under radical and nothing's squared and stuff like that. It's not going to be natural log because in order for that to be pulled off, you would need the numerator to be the derivative of the denominator, and that's not the case here. Well, it probably means that it's going to be some sort of simplification such that the rational structure disappears. Well, let's see if we can figure out what that is. And when in doubt, you can always pull it apart like this, okay? That may actually, if you can't see it here, perhaps putting it in that form will help you see it. Now, what needs to be recognized is the fact that 1 over cosine is, of course, secant. And so what this really was from the start was the integral of secant squared t dt. And if that's the case, we know that secant squared is the derivative of tangent. So if I'm taking the antiderivative, or the integral of secant squared, this just becomes tangent t plus c. Okay. And the same thing would happen on similar problems, like if you had secant v sine v over cosine v dv. You would look at that and think to yourself, gosh, that looks really, really ugly, until you recognize the fact that that portion of it simplifies into tangent, and then you have an integrand that is secant tangent. And that, of course, is a recognizable derivative, and you ought to be able to undo that pretty quickly, okay? Now, let's do 2 more. I think 2 more will probably suffice, especially since all of this is being supplemented by the virtual fourth videos that you already know about. Let's go ahead and do one with an exponential. Let's do 2e to the x minus, x cubed, okay, dx. Now, sometimes with exponentials, y'all get a little bit garbled. Maybe it's because y'all just haven't worked with them enough to really be comfortable with them, and that's fine. That's understandable. And if that's the case, then what you need to do is you actually do need to pull it apart into its constituent parts so that you can, when it comes time to integrate that exponential, just concentrate on that portion of it, right? And so what happens here is you're going to get 2e to the x, because if this integral is asking you what is e to the x the derivative of, the answer is e to the x. And then this x cubed becomes 1/4 x to the 4th and then plus c. Okay. Now, one last one before we sign off here. Let's go ahead and take a look at -7 over 1 plus x squared dx. Okay. Now, that's in a rational structure, and so there's really, only a couple of possibilities. You need to ask ourselves several questions. Does this simplify such that the rational structure is going to cancel out and disappear? It's just going to be term by term. And the answer is no. There's nothing in the numerator that's going to cancel with what's in the denominator, on top of the fact that the denominator itself does not factor. Okay. The second is this a natural log? Is what's in the integrand right here the derivative of a natural log function? And for that to be the case, the numerator would have to have an x in it, because the derivative of the denominator would need to reside within the numerator, and that's not the case. The next reasonable assumption we can make is that it might be inverse trig. And you say to yourself, well, that -7 is really mucking up the works, but then in a moment of brilliance you remember that that is a constant and can therefore be pulled out, and all of a sudden that integrand right here becomes very, very recognizable, and that becomes -7 arctan of x plus c. Okay. I'm hoping that this was enough examples, along with the talk that we had on Friday and the supplemental videos that are up at Virtual Fourth. I will be posting this video along with the answer key to what I assigned, and maybe any other supplemental information, as well as pointing you towards which video numbers in Virtual Fourth you need to be looking for. But I will be looking forward to our discussion on Tuesday. If you have any questions before that are pressing, by all means, send me a message in the Teams chat capability, and I will get back to you just as soon as I can. Okay? Well, I hope this has been helpful, guys, and I'll see you soon. Bye-bye.